In chapter 23, we have been looking at reactions at the alpha position of carbonyls. We talked about the acidity of that position. That is a position that might be more acidic than we would expect, considering that it's a carbon-hydrogen bond. The reason for that is that the conjugate base is stabilized by resonance. Once we deprotonate at that position, we can use that alpha position as a nucleophile. Okay? And we've looked at bromination reactions, we have looked at alkylation reactions, and we finished up last time looking at kind of some specific types of molecules, this malonic ester and acetoacetate, and these fell into the same type of trend that we could deprotonate an alpha position, we could do an alkylation reaction, but they were different in that we hydrolyzed then at least one ester and we did this decarboxylation reaction. Okay, so what we're going to start out with today is finishing up a couple of synthesis examples, and then we're going to go into chapter 24, and in chapter 24 what we do is we kind of combine everything we've learned about carbonyl groups so far. And I will kind of review that as we start into it. All right, any questions? All right, let's do a clicker then. All right, so let's pick up where... Put a lot of thought into this synthesis between Monday and now. All right? Okay, so what we're going to try to do is put two alkyl groups on a cyclohexane ring. Okay, so I guess one thing to think about is that in some way in the synthesis we have to have two reactive carbons next to each other, right? We have to put on two groups next to each other. So it's not just putting on a bromide like this and just doing a reaction at that center. We have to be able to do something next door. All right, so there are really two ways that I thought of to do this. How about you guys? How many ways did you think of? Zero? Hey. All right, so what is a way that we could...
Start with replacing the bromine with a hydroxy group and then oxidizing it into a ketone.
Okay, that is a way. So one way we could replace this with a hydroxy group, so we could... How would we do that? Okay, we can try to just do a substitution reaction. We could use maybe hydroxide. This might work. What's the competing reaction, though, would have to consider here? Elimination, right? So in fact, there's another way that we could do this if we ran into problems like that as well. What would that be? In 2 steps. We could do it, but we wouldn't have to worry about a competing elimination and substitution. Yeah?
So, enough with this reaction, but with previous reactions with the bromine on it, would you also just reacted with like the Vidics, and then just reduce the Vidic down?
Let's stick with this one first, and then we'll go to other options. Okay, yeah? Right, so another way to do this in 2 steps is we could, if we treat this with a strong base, maybe even a bulky one that won't do a substitution, let's say we use tert butoxide, something like this, then it will only do elimination, okay? And then we can just do a hydration reaction. H plus and H2O. Remember, it protonates on the double bond to give a carbocation, and water will attack that. So this would be a 2-step way to make it to that alcohol that we wouldn't run the risk of getting an elimination product as well. Well, a mixture of those. Okay, so then the suggestion was that we could oxidize, to use the weaker oxidizing agent that we can. And we have a ketone. Okay, so does the ketone give us the two reactive centers that we need on adjacent carbons? Yes, right? Because we have the carbonyl carbon and we have the alpha position. Right? So we can do reactions at either of those positions. Right? So if we want to let's put first the alkyl group on the alpha position. Okay, so I'm going to go up this way. I'm going to use LDA. So the strong base irreversibly deprotonates the alpha position, and then we could put on either the methyl or the ethyl group. Okay? So let's, just because I don't have enough room here on my screen, let's put on the methyl group. Okay? And then we usually would have to just kind of quench this at the end. All right, so if we do that, we've put on a methyl group onto one of the alpha positions. Okay? So now we have to put the ethyl group on, and we want to put the ethyl right where the ketone is. All right, so how are we going to do that? Yeah, we could use a Wittig here. That's one way. So if we wanted to put an ethyl group on here, then we would use this Wittig. This is 3. Okay, 2 carbon 1. Of course, we could make that just from bromoethane reacting with triethylamine, and then deprotonating that to form the ylide with butyl lithium. If we did that, we would get a double bond here like this, like this. Okay, so how do we get from that to the product? It's a hydrogenation reaction. Okay, so H2, probably palladium on carbon or something like that. Okay, chemistry from last semester. All right, is there any other ways that we could do this? Yeah.
You could use a Grignard from a ketone, or from the substituted right up there with the methyl.
Mm-hmm.
Ketone there. We can use a Grignard and then dehydrate it and then do a hydrogenation.
Okay, so another way that was suggested is that we could start out with a Grignard reaction. So we would use ethyl magnesium, let's use chloride or bromide usually, and then water after that. Okay, so that is going to give us an alcohol. Okay. Oops. Okay, so that, and we just added an ethyl group to that position, and we have a methyl group over here. Okay, so then the next thing would be to do a dehydration. Okay, we want to get rid of the OH, so we're going to get rid of water molecule. So let's just use something like sulfuric acid, right? Protonates on the alcohol, making it a good leaving group, comes out, it's a tertiary position, comes off to form a carbocation. Then we lose a proton, right, to form typically the most stable alkene. All right, so where is that double bond going to be? Is it going to be the same alkene that we formed from the Wittig? No, right? The most stable alkene is going to be the one that's most highly substituted. All right, so it's going to be the one that has the double bond between the two alkyl groups. Okay, so now we have an alkene. We want to get rid of the alkene, and so we just do the hydrogenation reaction again. H2, palladium, and carbon. Okay, both of these cases, you know, we're making two positions adjacent to each other reactive by having the ketone and the reactive alpha position, right? We do a reaction at one position. At the alpha position, we have to treat that or make that into a nucleophile to react with an electrophile. The ketone is an electrophile. We have to react that with a nucleophile. Okay? All right, so any other ways that we could do this? Any other kind of functional group that could bridge those two positions? Well, the two that has the alkyl groups, right? So we need to have something since, you know, we have two alkyl groups. We need to have some functionality that essentially somehow connects, right, two of these positions. We need to have two positions here. Before we had a ketone and an alpha position. Is there another way to do that? Yeah.
Some sort of oxidation?
Well, maybe. So we already have, that's exactly it, but we already have a functional group here that's bridging those two positions, right? So we can either hydrate this to there like we did, or we could make an epoxide out of that double bond, right? So we're just going to use some type, I'm going to draw it like this, a peroxy acid makes an epoxide. Okay, and now we want to get an alkyl group at one of those positions. Okay, so how do we add the alkyl groups? Not a Wittig, only reacts with ketones or aldehydes. A Grignard, good. So we could add, again, we could add either the methyl or the ethyl. Let's add the ethyl this time. Ethyl magnesium bromide followed by water. Remember, this is going to come in, it's a basic epoxide ring opening. This group is essentially going to come in on one side and open up the epoxide ring. Since this is symmetrically substituted, it doesn't really matter which end we're going to do that on. Right? So we get an ethyl group and an alcohol in the adjacent position, and then we are essentially, let's just do one more. So then we want to convert this alcohol to another alkyl group, right? So let's oxidize that. Okay, and a ketone, and then we have almost the situation up there. If I would have used the methyl here, we would have just made that compound in the upper right. Okay, so then we can do the Wittig and hydrogenate, or we can add the Grignard, do the dehydration, do the same chemistry as we did up above. All right, questions? I'm sure this was what you all had on your papers when you came in here today. Not that far. All right, so let's start with, which synthesis is this one called? What is that thing, the starting material called? That's the acetoacetate. So what stands out to you when you look at that product? You've got that ring, right? we learned how to make a ring with this, with the acetoacetate, right? So how do we do that? Yeah.
Use a dihalide.
Right, so we can use like a dye, we did almost exactly the same thing on Monday in that we can deprotonate this. We'll use methoxide, right? No, not methoxide, right. Let's use ethoxide and ethanol as our solvent. Okay, and then we want to use a dye, say bromoalkane, right, of the correct length to make that 5-membered ring. So how many carbons should I have in it? About 4. Okay, so let's just draw the products in 2 steps. We did this on Monday, right? After the first alkylation, oops, we get 1, 2, 3, 4. We get an intermediate like this. All right? Then the alpha position gets deprotonated again, and it just does an intramolecular SN2 substitution. So it goes again. And we make this 5-membered ring like that. Okay, so now what are we going to do? Right, so we want to get rid of that ester group, essentially. So we're going to use H plus, H2O, and probably heat this thing up a little bit. It's going to do the ester hydrolysis, followed by the decarboxylation. All right, and so then, everybody remember those 2 steps? Should I draw the intermediate? Okay, so the intermediate would be like this. We still have this methyl ketone, but we would have a carboxylic acid on this side. Right? This is after the hydrolysis, and then this would decarboxylate to form this ketone. Okay, so remember that the acetoacetate synthesis generates substituted acetone molecules. Okay, so now we have to get from this methyl ketone to that one over there. We have to, the chain on the right, we have to extend by 2 carbons. So it's a, yeah.
So we need to use the kinetics product?
The what?
We need to do it kinetically, so we need to use LDA.
Right. So what we want to do is we want to do an alkylation reaction and add an ethyl group onto the alpha position. And we have 2 possible alpha positions, right? We have the methyl group, and we have the alpha position that's part of the cyclopentane ring. We want to deprotonate on the less substituted side, so we want to use LDA because that gives us what we call the kinetic enolate. Okay, so we are going to just go straight up here. We're going to use LDA. Okay, it's probably going to be cold at 78 degrees Celsius. And then we're going to add an ethyl group as something like a bromoethane. Then we'll probably just have to quench that at the end. Okay, so what it's going to do, remember, is that it's going to deprotonate at this position here to form an enolate. And then that enolate is going to do an SN2 substitution on the bromoethane. And so we'll go straight to that product then, and we have formed this bond right here, right? So we extended that chain by 2 carbons. Yeah, question?
Just as review, how would we have done it if we wanted the thermodynamic?
Okay, good question. So if we wanted the thermodynamic enolate, we want to create a situation where enolate formation becomes reversible, right? So we usually want to warm it up. We usually use a little bit weaker base, but a base that also has a solvent system that has a proton source, so it can protonate and deprotonate. And so what we usually use is just like an alkoxide, something like even methoxide and methanol, or ethoxide and ethanol, something like this. That gives us the thermodynamic, more substituted enolate, and then we can add in, well, and then if we added the bromoethane this time, we would get substitution at the more substituted position. Yeah, Kristen.
Is the using that or methoxide, is the reason it doesn't do an addition on that ketone because just acid-base chemistry works faster?
Right, so yeah, so the question is, so we know that if we have methanol, but under acidic conditions, we can form hemiacetals and acetals to the ketone. All right, but those, yeah, really don't form well under basic conditions, because then we have to have hydroxide as leaving groups, and it doesn't work quite as well. Yeah?
Is there a reason we don't use LDA in like our first step with the, what is it even called, acetoacetate synthesis? Do we have to use the weaker like ethoxide?
Okay, so that's a good question. I think, so the question is, in the first step over here, this is kind of the traditional way that if we have the ethyl ester, we use ethoxide. And because, remember, this position here, the pKa is down at, what it was like, 10 or 11 or something. So it's really quite acidic, and this is strong enough to fully deprotonate that. So the question was, is there a reason why we don't use LDA? I don't think that there's really a reason. I think if you were going to do this with the cyclic one, you'd probably have to do it in 2 steps, though. Okay? With this system, it's kind of all under equilibrium, right? And you have enough base, you deprotonate once, it does its substitution, and then you can deprotonate again. Yeah?
At what point do we need to use THF or LDA?
Yeah, well, usually use THF, but I don't always worry about the solvent, whether you have it there every time or not. I just mark it wrong sometimes and not other times. Yeah, question.
Do we need to show both steps in this, or can we just show that it goes directly to the cyclic?
I think with these cyclic ones, with these alkylations, I'd like to see you do it twice. Just like if we were going to do 2 methyl groups, let's do it in 2 steps, okay? All right, everybody follow this one. All right, up here we're going to mostly use up all of our day to day just doing this. All right, so here's a malonic ester synthesis. But there's no acetic acid piece in there. Huh, we must have done more chemistry after that. Okay, let me just, let's work backwards a little bit here. What I'm going to suggest, and we'll try to figure out how to do this, is that we would make that from this.
Yes.
Okay, so at the end, we're going to add the double bond in. Okay, we're going to make this from this. Okay, and there's our substituted acetic acid. Okay, so everybody realize how we would get from malonic ester down to here. Right, so this is kind of the standard malonic ester synthesis. In fact, I think we probably did this one as an example. So we would use usually ethoxide in ethanol, and we want to form this bond here, so we need to use benzyl bromide. Okay, so this is going to go, I'm going to use these ETs for the ethyl again. Okay, we've added a benzyl group at the alpha position. Okay, so now we can get to here just by using H plus and H2O and heat. Okay, so this does the hydrolysis followed by the decarboxylation. Okay, so this is kind of the standard malonic ester synthesis. All right, so the question then is, how do we get from the carboxylic acid to the methyl ketone? All right, so this was kind of a thing that, similar to what was on the exam, right? This kind of chemistry. Can we just add a methyl Grignard and just substitute for the OH? No, why not? Right, so let's just go down this way. What if we add methyl magnesium bromide? What happens? Do we do a substitution reaction? Well, actually doesn't add at all. Right? Because remember that Grignards are very basic. So all this is going to really do is pull off the proton. So this just gives us acid-base chemistry. Okay, and doesn't go anywhere. All right, yeah.
Could you add SOCl2 followed by an organic grade?
Yeah, one good way to do this would be that we could convert this to the acid chloride. So we use thionyl chloride. That goes to the acid chloride like this. And then if we want to go directly from the acid chloride to the ketone, we can use those organocuprates. Okay, and they will just add one time. So we want to just add a methyl group. So our organocuprate looks like this with two of those methyl groups. What if we use methyl magnesium bromide at this stage? Adding to the acid chloride. What if we add methyl magnesium bromide to this acid chloride? Does it just go to that product? No? Well, it does go to that product, but what else happens? It adds again, right? You can't stop the Grignard from adding twice. Okay? Yeah.
So the carbonyl's not reduced to an alcohol with not a
No, not with a cuprate. So with the cuprate, all it's doing is an acyl substitution and stopping there.
Dr. Davidson,
Yeah.
there's about 10 minutes left.
Oh, dang. We're just in the heat of it here. Okay, so there are a couple of other ways if we want to get from this acid to an aldehyde, then we could add a Grignard, which would make the alcohol that we would have to oxidize. So how would we get from here to here? Huh? Yeah, we could, in fact, we could brominate at either the benzylic position with NBS, or we could brominate at the alpha position with, we got two different alpha positions though. We could brominate under acidic conditions. Maybe the benzylic position would be even better, and then do an elimination reaction. Okay? All right. So, that's the end of chapter 23.